Our topic is going on is a circle. In this topic, we have studied some properties of a circle, and now we are going to solve one example. In the given example, it is given that two equal circles intersect in P and Q. A straight line through P meets these circles in A and B. Then prove that QA equal to QB. So first of all, we will see our figure deeply. Here it is given that two equal circles, means the circle with the center O as well as the circle with the center O dash, both are equal, means radii of both the circles are equal, means both the circles are congruent circles. These two circles intersect each other in a point P and Q. These two circles intersect in a point P and Q. A straight line through P meets the circle in A and B. There is a point P through which the line AB is passing and it intersects. The line intersects the circle with the center O in a point A, and the line intersects the circle with the center O dash in a B. If such a condition is there, then we have to prove that QA equal to QB. Means QA and QB both are equal. Here there is a construction, means we have joined AQ and BQ, and on the arc PQ there is a point D, and this PDQ is the arc of the circle with the center O dash, while the arc PCQ is the arc of the circle with the center O. Here, to solve this question, let COR, means a circle with the center O and radius R, and circle with the center O dash and radius R, be two equal circles. Just now I have explained that both the circles are equal, means both the circles are congruent since their radii are equal. So here COR congruent CO dash R. Here it is seen that PQ is the common tangent to both the circles. This PQ is tangent of this circle with the center O dash, as well as PQ is the circle tangent to a circle with the center O. So it is the common tangent. We know that if tangent are equal, then their corresponding arcs are also equal. Here, since PQ is the common tangent, then arc PCQ equal to arc PDQ. So here we can write arc PCQ equal to arc PDQ. And we know that if the two arcs are equal, then the angles, that is the angle, central angle, it should be equal. So angle QAP, here angle QAP equal to angle QBP, means QBP, that is angle A and angle B, both the angles are equal. And if we consider the angle ABQ, then the two angles of a triangle are equal, and we know that if the two angles are equal, then such a triangle is an isosceles triangle. We know the property of an isosceles triangle, that is the sides opposite to equal angles are equal. Here since A and B are equal, then the side opposite to angle B is AQ and the side opposite to angle A is BQ, and therefore we can say that AQ is equal to BQ or QA equal to QB. And the reason is that sides opposite to equal angles of an isosceles triangle. So in this way we have proved that QA equal to QB. Now we have our new point in this topic is that arcs and angles subtended by them. Arcs and angles subtended by them. So we will see one theorem which is very important, because its statement or this property is very important in our topic. That is, theorem is that the angles subtended by an arc, the angles subtended by an arc of a circle at the center is double the angle subtended by it at any point on the remaining part of the circle. Means if we consider a circle and let AB is arc. For example, we will consider AXB. AXB is an arc. Then that is the minor arc. Then AYB will be the major arc. Now it is given that the angle subtended by an arc means angle with the center O. If we take then the angle subtended by the arc with the O is angle AOB. Angle AOB. So it is the angle subtended by an arc of a circle at the center. At the center. So that is the angle AOB is a double. That is double of the angle subtended by it, means arc, at any point on the remaining part, means remaining part excluding AXB, the remaining part of the circle you can take here, any point you can take. For example, if we consider the point R here and join with A and B, then the angle ARB. So angle ARB. So here we can write here double the angle ARB. So here it is given that the angle subtended by an arc of a circle at the center is double. It is double the angle subtended by the same arc at any point on the remaining part of the circle. Means you can take any point on the circle and join with the end points, that is the A and B, then you will get the angle ARB. So angle AOB, major central angle AOB, is double the angle inscribed with any point on the circle. So here we have drawn a figure of a circle with a center O, and PQ is the arc, and the angle inscribed by the arc with the center O is POQ. It is POQ, and the angle subtended by the arc to any point on the remaining part of the circle, that is R, so it will be PRQ. So we have to prove that POQ equal to twice angle PRQ. So here it is given that PQ is an arc. PQ is an arc of a circle COR, and R is the point on the remaining part. Means excluding the arc PQ, we have to take any point R on the remaining part of the circle, that is arc QP. We can say the remaining part is QP, and to prove that angle POQ equal to angle POQ is equal to twice angle PRQ. And now there is a construction, means join OR. Here we have joined OR and produce RO. We have produced RO to a point M outside the circle. Here we have taken the point, means we have produced RO and taken the point M outside the circle. And now we will write the proof. That is, we know that an exterior angle of a triangle is equal to the sum of the interior opposite angles. If we consider the figure here, it is seen that in a triangle POR, here POM is the exterior angle of the triangle POR, and we know that the measure of the exterior angle is equal to the sum of its interior opposite angle. Here these are two angles, that is OPR and ORQ. These are the interior opposite angles. So we can write angle POM equal to angle OPR plus angle ORP. So here we can write in a triangle POR, angle POM is the exterior angle, and therefore angle POM equal to angle OPR, this is angle OPR plus angle ORP. But we know that OP and OR are the radii of the same circle, and therefore they are equal. And due to this, triangle OPR is an isosceles triangle with equal sides OP and OR. And we know that if the two sides are equal, then angles opposite to equal sides are also equal, and therefore we can say that angle OPR equal to angle ORP. And now angle POM can be written as angle, instead of OPR we can write ORP plus angle ORP. That will be angle POM equal to 2 twice angle ORP. That is our equation number 1. Here we have considered the triangle OPR. Now we will consider the another triangle, that is OQR. Again, angle QOM is the exterior angle of the triangle QOR, and again we will apply the property of exterior angle theorem, that is the measure of exterior angle is equal to the sum of its interior opposite angle. So again we can write here angle OQR is equal to, or is in a triangle OQR, angle QOM is exterior angle, and therefore angle QOM is equal to angle ORQ plus angle OQR. These two angles. But again, OQ and OR are the radii of the same circle. So triangle OQR is an isosceles triangle, and therefore the two sides are equal, and therefore its opposite angle or their opposite angles are also equal. So we can write here angle QOM is equal to angle ORQ plus angle ORQ, and that is equal to angle QOM is equal to twice angle ORQ. That is equation number 2. Here, adding equation 1 and 2, we can write angle POM means the left side of equation 1 is added to left side of the equation 2. That is angle POM plus angle QOM is equal to, now adding RHS of both the equations, we will get twice angle ORQ plus twice angle ORQ. Twice angle ORQ plus twice angle ORQ. Here it is seen that POM is this angle plus QOM is equal to angle POQ. Now taking 2 as a common to the RHS of the equation, we will get 2 into bracket angle ORP plus angle ORQ, and we know that angle ORP plus angle ORQ, it will be angle PRQ. In this way, we have proved that angle POQ is equal to twice angle PRQ.